got some questionable news.
Okay, we'll wait on that.
Oh.
Because I got two Sean's, and I got an email from Sean, this is bad news, but it wasn't you.
Oh, yeah. Well, you got an email from me,
Yeah.
but it shouldn't show up as Sean, it should show up as Rondell.
Nope, then it wasn't you.
Oh,
Okay. So that's good news.
I have some questionable, on some news.
Oh,
It's for Leo, like mine said, you posted our final grade.
well, I've been playing around with that, trying to learn Leo, and just ignore that.
Just making sure.
Yeah,
So now it's just okay news.
yeah. My learning curve. Neat shirt,
Huh?
a neat shirt. You
Oh,
have.
thank you. Try to have a little fashion sense of it.
I like it so much when you work on the question and then you find the answer yourself. That's gold.
And I found the video I'm gonna share too.
Hmm?
I found the video. I'm gonna share.
Good for that, too. When we start to concentrate on this
I just figured out how to use the T distribution. I just now, but I didn't watch the video before, because I hadn't finished watching the video yet, so I found one that shows you how to do it. So, do you know how to use the T distribution? What about it?
Figure out how to do it first.
And which one? I did lane first, but I look at a big wheel.
Well, I can try that too.
In some ways, it was better to do Lukowski first in this one.
Oh, normally I do lane first too.
Yeah.
I haven't finished neither one.
No, as long as you're 90% through, that's all we expect by Tuesday.
95% confidence interval on the mean based on the following sample. So did you find the mean of these?
Yeah, I did that.
And you got.
You found the mean of the sample, right?
So
Of
it's,
all those ones that.
yeah, it's 14.2, right?
Right.
And then since it's 95 confidence interval, your z-score would be 1.64.
1.96.
1.96
Wait a minute.
for 95? Oops.
See, how do we get that?
So if you find 95% in here,
You don't find 95%. Okay, you can find 95% in there, that works.
right?
Yeah, that works. Oh, no, you don't find 95% in there, that's wrong.
I did the,
It's a good thing we're having this class
Yeah.
I
tonight.
did the thing
I
where,
was very
I did the,
confused every time it said,
I forgot what it's called, but the standard deviation over the sample, square root of the sample. So I did 2.8, at the end of that, you get 2.8 divided by 3, you get 0.933.
yeah, since it's confidence interval on the mean based on the following sample. So we have the mean,
Hi,
which
no.
is,
Okay, we'll straighten it out.
yeah, I'm reading it now. I think this, what I messed up on was the 95.
It's not 95.
So, yeah.
It's really hard to learn statistics from a book. Really hard.
Oh,
The only harder thing would be trying to write a book about statistics, hoping that people would learn from people fast.
Oh. So 95% of 1.96, which means this is what?
But why is it 1.96? Did you figure that out?
well, I get the 1.96 would be, that's the
Then
two
tell
standard
her.
deviation,
That's right.
but I ain't using any scrubs to prove that.
Well, between the two of you, you got the problem wrapped, because you're doing different parts right.
Yeah, but I didn't use that 1.96 at all.
I know how to use the formula, I just don't know where the number comes from.
What formula are you supposed to use? I don't use two numbers. Like, I ended up with this
You're supposed,
interval that clearly must be terrible.
you're supposed to figure out the margin of error, which is plus x
Hi,
plus
Tayo,
or
welcome
minus
to Tuesdays.
z times the
That's
standard
your
deviation
deep winter
divided by
coat?
the square root of that,
Yeah?
which would give you,
For anyone else, it's a cool summer night. What's your metabolism, off the charts or something? Just don't get cold, do you? Look at his t-shirts and windbreaker.
see, this is your confidence interval, x bar minus the square root of, yeah. Where I find that most of the formulas, and then I just use them in.
Hi, Karen.
Hello, hello. I think I'm going nuts in the hallway, I swear I hear singing and it's like,
Singing?
yeah, I'm going.
Was
okay.
it good singing?
Well, it would pass.
That's good then. It's a plus. It's a plus.
Confidence
Sounds like
interval has a formula.
Weird.
It says x bar minus EBM and x bar plus EBM, and EBM is your margin of error. So you use the margin of error formula to calculate the EBM, and then you add or subtract it from your x bar of your sample.
printed out the problems for your ease of use.
Oh, I did as well.
Already we do the same thing, that's just,
I sorted it out. How about that?
it's a sorted task, I know.
Yes.
Might just be easier to go through some.
Hmm. 5 minutes? Keep going. Hmm.
Thank you for this.
You're welcome, ma'am.
Yeah, I like it a lot.
Me too.
Would you be mad if I kept my bad work in here?
Your what work?
My bad work,
No, I wouldn't be mad.
so
No,
just don't read it.
there's no such thing as bad work, so,
I do write it, read it, I'll write it on this.
no, there's no worry about that in the slightest.
The formula's right, just the number.
Mm-hmm, mm-hmm. Tayo, are you on special, do you watch what you eat?
To an extent, yeah.
What is your major items?
That I eat, that I
Yeah,
eat,
yeah.
fish.
Pizza and hot dog,
Yeah.
fish,
Fish, chicken.
fish chicken, yeah. Green beans and,
Yeah.
did you know a lady named Melton?
Uh,
Well, she competes in the bodybuilding, usually wins it for the ladies. And she took the math course, and she lived on green beans and chicken. She was strict because she was competing. And, yeah, a lot of green beans. So you're trying to watch the body fat, eh?
Yeah.
Yeah, that's what you need. So do you think that the ideal body fat is less than 5, or that starts getting dangerous?
5%.
Yeah,
It's pretty low.
that's pretty low already, yeah, right. Yeah, I think 0 is next thing to death, right? Yeah. But double digits is bad, right?
I think it's just a very low person.
On the person. Okay.
You
seconds. Commence. Okay, on. Are there any urgent topics, questions, remarks to take right now? We'll take the questions later, but just about the course. The course is going very well, which is good news to me because we're starting so many new things. Such as this hybrid format and live streaming. They wait until we start. And laugh all the way up. So has anyone considered the wisdom of building the Ed building next to the runway? There's some very quiet areas on base. Like over by the recycle center.
Except now you'd have to listen to all the dogs barking.
Now these days you would. This is centrally located, I grant you that. So everyone does know why the Air Force has better clubs, streets, golf courses, and facilities than the other service branches.
Well, I can tell you the Navy theory,
Go.
because my husband was in the Navy. He
Got
said
it.
the reason that the Air Force has the best facilities is because they build all those first, and then when they run out of money, they say, we have to build the runway, so then they get the extra money to build the runway.
That's the story.
Yep. And the Navy
Big-
puts all the money in the ships, and then they go, we need money for support, and they go, psh, families aren't issued.
Exactly. So they build the runways last, so
Yeah.
they go to Congress and say, well, it's all finished except the runways. We're out of money.
Yeah.
So
The other
Tough spot.
branches of service need to get smarter.
it works. Okay, so back to statistics. This course is going to be a success. And we did discover, which is why we're here today, that it can't be taught as a hybrid course. It needs to actually have this extra session. So that was some wisdom gained. And with that in place, I think we have clear sailing, green light all the way to the end. So one item, Paul is expected to talk his oral presentation on Thursday. It would be nice if we had another one in the queue in case we had time for two, or in case Paul pulled a Paul trip and didn't do. But he was ready last time, so he couldn't get sick. Things happen. So does anybody else see themselves as being ready this Thursday in 48 hours? Okay, then we definitely need people to be ready for next Thursday. And there's no longer any choice about this because I've given a deadline of this Saturday for people to choose their topics. Now, if need be, we can give some of those talks in this Tuesday session. And if all of that fails, then we do have that last makeup session on the last Friday of the term. What else would you want to do on the last Friday of the term, except, come and give your oral presentation in STAT 200. So it will work out, but the sooner things are done, the better, because things typically jam up the last week, especially if you're taking other courses. So we want to get that done. Now, did everyone print out those 3 help sheets that I gave you? One was a flow chart, a full T-table instead of the skimpy one that Lane gives you, and some other stuff. So Tayo, did you get those printed out? Okay. Did you see them?
No, I didn't see
Do you read your email, Kyle?
I do. Is it already fine?
No, later.
Alright.
Okay, good, this is not the time to do things that should be done before. I figured if I sent it to you an email, that it would be noticed and done. So now, as some of you know the hard way, it's become necessary to dock points if you don't log in and read the news, because the quality of the course was suffering, people not knowing things they should know, or printing out documents they were expected to print out, which were also in the news. So, you're going to get docked half a point each time you fail to read your news for 2 days. Some people have had that happen already. So we do need you to log in and keep up with the course. So that was the other little bit of news about the news. Goes through Iwakuni too, and that's the end of my announcements. So any feedback on that? Okay, it's time to teach. The topic for this week is called estimation. And the first subtopic is called interval. And depending on the interval that I ascribe to my estimation, I can have a certain confidence level. For example, if I say that Sean, next test grade is going to be between 0 and 100, what's my confidence level? 100%, agreed? So you see how the confidence level goes along with the interval. If I have a whopping big interval, I can have a whopping big confidence level. But suppose I want to say that Sean's next test is going to be between 50 and 70. What's going to happen to my confidence level now? Is there any, can I say that with 100% confidence? No, it's going to come down to maybe 80% confidence, or even lower, agreed? So as you shrink your interval of prediction, then you also reduce the amount of confidence you have in it. Now suppose I say Sean's next test is going to be in the interval of 63 to 65. I'm going to have a confidence level of about 8 or 9% on that one, agreed? So confidence level goes along with the interval of your prediction. Now let's look at a couple of other terms. Suppose I take the interval from 50 to 70. Then this would be the upper limit of the interval, and this would be the lower limit of the interval. Now my best guess is going to be what single number? 60, agreed? My best guess is going to be 60. So this is your best guess. And if you're given the interval limits, then it's equal to 50 plus 70 over 2, which is the average of the two, isn't it? So if I give you an interval, you can always find the center point, which is the straight average of the two ends. So this is going to be the best guess. It's also called the point estimate, a single point of your best guess, agreed? So now, the interval from 50 to 70, which is here described, can also be written as 60 plus or minus 10%. Am I designating the same interval in that format as I did from 50 to 70? 60 plus or minus 10%, agreed? So 10% is called the error from your best guess. The error from your best guess is the 10%. So then the error in terms of upper limit and lower limit can be found how? If I give you the upper limit and lower limit, can you tell me how you would find the error? Think. I'll does that 10 come out of the numbers 50 and 70? It's very much like the best guess. The best guess was 50 plus 70 over 2, and the error is going to be just slightly different. It's what? 70 minus 50 over 2. Because, is this not the error right here? Is that not the error? And it's halfway across the space, isn't it? So the distance across the space is 20, 50 minus 70. So you break that into two pieces. There's an error to the right and an error to the left. So there's another error over here. So I can give you this information in various formats. And you have to be good at going back and forth between one format and another. So suppose I give you that I'm going to have a point estimate of 40, and it's plus or minus 5%. Now, it's very easy when I give it to you in that form. What's the point estimate? 40. What's the error? 5%. Now go backwards. What's the upper limit of the interval? And what's the lower limit? 35. So you see that this up here is P plus E, and this down here is point estimate minus the error. Agreed? So if I give you the point estimate and the error, then you can reconstruct the interval. Okay. So let's try one more time. If I give you the interval, from 30 to 60, and I just give it an ordinary interval notation, okay? Now, what's the error? What's the error? 15. Tayo, 15? The error is 15. This is the upper limit, lower limit, and the error is upper limit minus lower limit over 2 equals 15. And what's the best guess or point estimate? 45. And P is equal to upper limit plus lower limit over 2, or 45. So you can go back and forth between one format and the other. And the basic point that we started with is in effect, and that is, as you shrink your interval, you also shrink your confidence. And as you expand your if you want high confidence, can you do it with a small interval? If you want high confidence, then you have to give some ground and accept a wide interval if you want the high confidence. Now, let's relate this a little bit to statistics. If I have a population, a normal distribution, and it has some mean mu, and if I start taking samples out of that, and I plot the distribution of the samples, then it will have some mean of the samples, mu x. And it's a fundamental reason why polling works. What's the relation between the mean of the samples and the mean of the population? They're equal to each other. This is why polling works, the only reason why polling works. Now, this is a very real distribution of the population. This is a hypothetical one. It only exists in imagination, and I'll show you why it only exists in imagination right now. If we look at Misawa Air Base, which has a population of 10,000, and if I start taking samples of sample size 100, then the number of samples, different samples of size 100 that I can take out of a base population of 10,000 is big N to the small n. So it's 10 to the 4th power to the 100th power, which is 10 to the 400. So I can take 10 to the 400 power samples of size 100 out of this base. And that is a 1 with 399 zeros after it, which is a lot of samples. But that complete set of samples is what I'm graphing here. So do you think everyone's actually done this, or is this a hypothetical mathematical distribution? It's a hypothetical mathematical distribution. And you can prove rigorously that this mean is equal to that mean, even though you can't produce all of the samples. And for those of you that took the trouble, the proof was provided last week in lectures by your instructor, and that's why it's out there. Now, let's examine this a little bit more. What I want to do is to take one sample. Here it is right here. I'm going to construct one sample. Okay? Now, that one sample has a mean. And I would like to be able to say that the mean of the population is the same as the mean of my sample. But you've actually got no basis for saying that, true? But I can say the following. If I box off a 95% area under this normal distribution, true? Then if my sample is randomly distributed, then it's going to occur in this region under the curve with a 95% probability if it's a randomly chosen sample, agreed? Now, if my sample is random, then I can say that it is in this area of this curve 95% of the time, or with a 95% chance, agreed? So there's a 95% chance that my sample is in this area, agreed? Now, what is the width of this area? It's 2 standard deviations, is it not? Because in a normal curve, what is the amount of area between minus 2 standard deviations and plus 2 standard deviations? Is what percent? 95%. So the converse is true. If you want to have a sample that's in this 95% of the area, then it will be in this region of 2 standard deviations, plus or minus. Plus or minus 2 standard deviations, agreed? From the mean itself. So therefore, I know that if this is a random sample, that it is with 95% probability no further than 2 standard deviations from the mean, if it is a random sample. So with 95% probability, my single sample is within 2 standard deviations of the mean of all samples. But what does this say? The mean of all samples is also the mean of the population. So I can take one random sample, and because it's under a bell-shaped curve, I know that the distance between my mean and the center of the means with a 95% certainty is at most 2 standard deviations. So therefore, I know that the mean of my one sample, because this is also the mean of the population, the mean of my one sample is also within 2 standard deviations of the mean of the population with a 95% certainty. And that's a fundamental reason why polling works. So let's take that in a large graph and look at it one more time. This is the sampling distribution. This is the distribution of all samples. So it has a mu sub x bar, which is the same as the mu of the population. Now, this is the mean of all possible samples. and it's also the mean of the population. Now, if I take one random sample, then is there not a 95% probability that my random sample is in this space? So what is the maximum distance that a sample in this space can have from the mean? This is the maximum separation it can have from the mean and still be in this space, agreed? So this is what we call the error. This is the error at 95%. It can be at most 2 standard deviations away with 95% confidence. This is called the error. Now, so in the worst case, my X bar is going to be out here. And this is a distribution of sample means, so this is the distribution, the standard deviation of the sample means. So now, if this is a point under the curve, it has a z-score, agreed? And the z-score is equal to x bar minus the center point divided by standard deviation. This is the definition of z, agreed? Now, I've chosen to work with a 95% confidence. So therefore, I have chosen a z of what? What's the z value of this point?
1.96.
1.96, or loosely speaking, 2. The z value of this point is 1.96, agreed? So that is going to be 1.966. Now, this right here, is it not this distance? This is my x bar, the worst possible case, agreed? From the center point. So it is equal to E, the worst possible case. And for a sampling distribution, we know that sigma sub x bar is equal to sigma of the population divided by what? Square root of n. So this becomes the sigma of the population over the square root of n. Now, if you cross multiply this, then what you produce is that E is equal to 1.96 sigma over the square root of n. Now, is there anything special about my choice of 2 standard deviations? I just chose that as an opening example, agree? So let's take a more general case. If you want to have some probability of confidence level, then let's suppose that your probability would be, say, 90%. So if you want a 90% confidence level, then what is your non-confidence percentage? 10%, agreed? That is what we call alpha. So in this case, it's equal to 10%. So for this chosen confidence level, my alpha is 10%, agreed? Now, if I want that 90% to be centered on the graph, and it's right here, so this is 90% in the middle here. So, this is the question I now ask. What is this percent, and what is that percent?
5 each.
Sorry?
0.0.
Each one is 5, is it not? This is what you did wrong. Each one of these is 5%, agreed? Okay. So this point right here has a certain z-value. It's a z-value that goes from here all the way to the left. This has the same 1 minus, agreed? So if you want to know this z-value for 90% confidence, what do you look up in the table? Do you look up 10% or do you look up 5%? 5%, that's why it's called z alpha over 2. Because it's got 2 ears. So if you want to know the z-value that marks the boundaries of an alpha uncertainty, you look up z alpha over 2 in the table, because it's got 2 ears. So let's go back to our 95%. If you want confidence level of 95%, then what's alpha equal to? 5%. And what's alpha over 2 equal to?
2.5.
2.5%. So this is going to be z of alpha over 2. And this is going to be 2.5%. And over here is also going to be 2.5%. And this is z of plus alpha over 2. So now what's our error going to look like here? Again, we have our maximum error, do we not? And the z-value is always going to be, this is now going to be our x bar, and this is going to be our mu x bar, and the maximum distance at this confidence level between x bar and mu x bar is what the error is. So if you just write down the equation for z, you see that z of alpha over 2, this point right here, is equal to x bar minus mu x bar over sigma x bar, and this is equal to e over sigma x bar is z alpha over 2. So if you cross multiply again, you see that the error is always z alpha over 2 times sigma over the square root of n. And we produce the formula that is just given to you too many times, sigma over the square root of n times z alpha over 2. So we produce the error formula that goes with any alpha over 2. Where does alpha over 2 come from? The very first thing somebody does is they state the confidence level that they want to work with. Once a confidence level is stated, does that give you alpha over 2?
Yep.
If I give an 80% confidence level, what's alpha over 2? 10. So if you want to get the z that goes with that, you look up 10 in the table. That's why we call it alpha over 2, because there are 2 ears. And that alpha uncertainty is divided into the ear on the left and the ear on the right. So that's where the formula comes from. The amount of error is given by the z-score for alpha over 2 times the standard deviation of the sampling distribution. And from this you can answer all kinds of questions. If you want to keep your confidence level constant, if you want to fix that, that means you're fixing alpha over 2. If you fix alpha over 2, what happens to the amount of error that you have if you increase your sample size? This n goes up and up and up, agreed? But it's in the denominator. So the overall value goes down, down, down. So if you fix your confidence level, increasing the sample size reduces your error. And in fact, if you take your sample size all the way up to the entire population, then of course your error goes to 0. Because then you are talking about the mean of the entire population, which is not a random sample. It is the population. So it goes to 0. And the other thing is true, if you keep your sample size the same, if you keep your sample size constant, but you want to decrease your confidence level, you want to go from 90% down to 80%. So if this goes down, then what's going to happen to If your z goes to a smaller number, if your probability goes to a smaller number, then your z-score is also going to go, probability is going to go down, your z-score is going to go down. As your z-score goes down, then what happens to your error? Also goes down. So if you want smaller confidence, then you get a smaller error. Smaller confidence amount. That is not interval.
I thought it's the
No, it's
opposite.
the other way around. So why is it
Yeah.
coming up backwards?
Yeah, I thought-
Let's go back to the graph and figure it out. Okay, now, if you want to, decrease your confidence, agreed?
yeah.
So you come down to here, and you have a decreased confidence amount, and, your error is going to certainly get smaller for a fixed size n. Your error is going to get smaller for a certain size n. I, because,
That will affect the sample size as well.
sample size has been fixed, it's not changing. So fixed sample size is not changed. Okay, so now let's look at this. Your error gets smaller as you decrease your confidence level. The absolute value of your error gets smaller as you make your confidence value smaller. Yeah, well, that would make sense. As your confidence limit goes down to 50%, then your error is also going to go down, but your interval gets bigger. Your interval gets bigger, but your error goes down. So how can that happen? There's something missing here. Okay, your error goes down if you're willing to take a smaller confidence. If you're willing to take a smaller confidence amount, then, and the same size sample, a smaller confidence amount and a lower confidence with the same size sample, then your error is going to go down. It is going to go down, that's true. If you have the same size sample and you're willing to work with a smaller confidence that you want, then the amount of error will decrease. So the question is, how does that fit with what we opened before? Well, we opened with just one person, with one test score. So we didn't go into statistics. We just had a single person with a single test score. And with a single person with a single test score, if we wanted to have more confidence in our prediction, then we would have to have a wider interval for that test score. But when we're comparing one sample back to the population, if we're willing to work with a smaller confidence level, then we will reduce the error. And that's also reasonable. If you take one sample and you want that sample to represent the population with a 95% confidence, will you be doing this with a large error or a small error? It would be a large error. But if you're willing to come down to representing the population with a 50% confidence, then you can do this with a smaller error, because you're less confident. Because you're less confident, so your error for it to come in at that confidence level, then your error is doesn't have to be large. You don't have to be able to tolerate a large error. If you want a high confidence, you have to be able to tolerate a large error. If you want a low confidence, then you can tolerate a small area. Okay, so that did straighten out. Now, I think it's good now we're going to go direct to problems. So we presented the concepts, the theory here. Question on this or? Okay, so any questions on the presentation, the concept? Okay. Now, the same thing holds true for proportions, but for right now, I've just presented it for means, so I'll hold off on the proportion for a while, and let's try a few questions. So starting with Lane. Let's start with a chosen one, which illustrates the calculation. So let's start with number 11, because it's such a standard problem, agreed? So we're in lane number 11. Okay, did everyone, Nux, here, we printed these out for you, in case you didn't print them out yourself.
Did you have another copy? I don't have Lane printed yet. I was just working at the other one.
Okay, a population is known to be normally distributed with a standard deviation of 2.8. So as Kayla likes to do, we start a parameter list. Sigma of the population is 2.8. And we want the confidence level to be, confidence level is 95%. That means alpha is 5%, and alpha over 2 is 2.5%. So we build in a little confidence level. Now we have the sample of 9, so n is equal to 9, sample size. And the sample itself has the following members into it: 8, 9, 10, 13, 14, 17, 16, 17, 20, and 21. So we can compute our sample mean. What is the sample mean?
14.2.
14 point what?
2.
14.2. Okay. Now we want to compute the confidence interval. So what we know is that the error is equal to z of alpha over 2 times sigma over the square root of n. Now, z of alpha over 2 is 1.96. All in favor of that? I loosely have been calling it 2, but you look up 2.5 in your table, and you're going to get 1.96. Sean, okay on that?
Yeah,
Well, let's take your table that you have, and find 2.5. And I'll do the minus 2.5 because it's on the left side. It's a little bit easier, you don't have to subtract from 1. And 0.25. And I found it. And indeed, I get 0.25 is exactly minus 1.96. Okay? So we found it. It's equal to 1.96, and it's 2.8 over the square root of 9, which is roughly 3. So if we do this calculation, we find that the error is what number?
1.829.
1 point what?
1.829.
1.829. Now, this is the difference, the maximum difference between our sample and the population mean. So we know that our sample, x bar, is equal to 14.2. So on the right side, we have x bar plus e, and on the left side, we have x bar minus e. So what do we get on the right side?
16.
Sorry?
16.0293.
60.04, that's what I got.
That's good enough. What do we get on the left side?
12.37.
Okay, good. So this is our interval. If you want to write it in interval notation, 12.37 to 16.034. This is the confidence interval that we have at this 95% level. So now we make the audacious step. All we really have is the sample of the mean of the sample. But we say that the mean of the population is also in this window with a 95% certainty, because the maximum distance that our sample with 95% certainty would be from the true mean is 1.96. But if it is 53 meters from here to Burger King, how far is it from Burger King back to here? 53 meters, granted? So if our sample is within 1.96 standard deviations of the mean, it means that the mean is also within 1.96 standard deviations of our sample. So we can go in the other direction just as well. So we can make the statement that the mu is between 12.37 to 16.034 with 95% confidence. Now that doesn't mean that the probability of finding the mean in this interval is 95% on any given measurement of a sample. What it means is that of all of the samples that we take, then the mean will be found to be in this interval 95% of the time. 95% of the time, we will find the mean of the population in this interval. The other 5% of the time is going to be out in the ears someplace. So it's a technical point whether you say that the mean is in this interval with a 95% probability, or you say that the percent of the samples that we take will find the mean in this interval 95% of the time. And all of the authors of the textbook prefer the second, but in general talking, we usually use the first, so you take your choice. So we did number 11, and now you want to go to the 99% confidence level using the same data. The only thing that's going to change is z of alpha over 2. So now, if you want 99% confidence, what is alpha? 0.01, agreed? Therefore, what is alpha over 2? So find your table, and I want you to find 0.005, and I want somebody to tell me what is the corresponding z-score. And first, let's get Tayo. What's the corresponding z-score? You got your table.
Is that the one you sent through?
No, this is the one I sent to you 2 weeks ago. Lynn, you have an extra, or I have extras? Okay. Have you got one now? Okay, so look in the table. In the body of the table, I want you to find 0.005, 0005.
For which one?
Oh,
And go with the minus score, it's easier to find.
maybe the 2.5.
Negative, wrong. Well, maybe I'm doing this wrong. So what we have is 0.05%.
He's close.
No.
Negative 2.57 is 0051. And the one after is 0049.
Yeah, okay, I had too many decimal places, so I grant you right on that one. Okay, good. Okay, so
I'm
Doug, did
confused
you
here.
find that one okay?
No, I did the problem, but I got different answers than what you have on the board. I mean, in order to get the x value over there, the x bar, do we have to go like 2 places or just one?
2 places.
2 places. What about you got 14.2?
Oh, don't worry about that. If you're slightly different, you get full credit. We don't look for precision here, we just look for correct steps.
Okay, and I'm still having problem with the z-score. Like, I don't know, maybe I'm reading it wrong. Like the one we just talked about, the 2.5.
2.5?
2.5.
Yeah. 2.5%. 2.5% is equal to 0.025, agreed?
Yes.
So now in the body, I want you to find 0.025.
So it should go to negative.
Yeah, go to, well, no, just find .025, it's only gonna be one place. From these numbers in the body, .025. Did you find it? .025.
2.2.
So for 99, we're going to get point two, 2.57, or 2.57. Okay?
So 0.025 will be 1.9. The Z scope.
Repeat that?
The 0.25.
Yes, it would be minus 1.96.
Okay, 1.9.
See how to read that?
Okay.
Okay.
Well, but for the other one that you were saying, we find the, .005.
It's half of
which is
1%.
5. So do you say that it's negative 2.707 or just 2.57?
It depends on your personality.
So this is,
It would be
this is this
um,
side and this side, and this is just one side.
2.5,
So then he says go to the negative, because it has the extra. So if you go to the
7,
negative and find
it could be
0,
2.5,
0,
8, or it could be 2.575. Depends on your personality.
Okay, so when the top says 0.0 and a number, we just ignore the 0 and add the number.
No, you add it to the number in the column.
Right,
Now,
okay.
here in the column, you've got 2.5,
Right.
and up here, you've got .07.
See, that's why I didn't understand why we weren't putting the 0.7 to the 2.5, we're
You
just
are.
adding the 7.
That's the Z-score.
You align the decimal places.
Gotcha.
You align the decimal places. So this top is the second digit.
It's-
Right, gotcha.
The first digit is in the left column, so the top gives you the second digit.
Got it.
You can't learn statistics.
It'd be 2.58 plus minus 14.2.
Yeah, after you do, yeah. Yeah.
Okay, so we're all on board. That was the easy one, the freebie. Hmm?
Oh.
Okay. So I'm looking for another standard type, so that, okay, so 15, 16, 18, 19. Well, Ilkowski also has standard types, we can go to her. So let's go to Ilkowski and find a standard type. So Ilkowski, 1, 2, 3, 4, and 5. So Ilkowski, number 1, use the following information to answer the next 5 exercises. The standard deviation of the weights of elephants is known to be approximately 15 pounds. So Kayla Jo likes to immediately make her parameter list, doesn't hurt. So sigma in the population is 15 pounds. We wish to construct a 95%, so we know alpha equals 5% and alpha over 2 equals 2.5%. And we also know that z alpha over 2 equals 1.96 because we've done that one so many times. So now we wish to construct for the mean weight of newborn elephants. 50 observations were taken, so n equals 50. The sample mean is 244 pounds. X bar equals 244. The sample standard deviation is 11. So we've got all our parameters on the board. Identify the following. A, X bar is equal to what? Anybody?
244.
244. Alpha equals
15.
15, and N equals.
50.
Okay, now in words, define the random variable X. Nux, what is it?
Is it alpha or sigma for B?
Sigma. Sigma. I'm sorry. Sigma, I mispronounced. Sigma's 15. Okay, good. Now, Nux, in words, define the random variable X. In this problem, what is X standing for?
The
Answer,
random
the weight
variable
of one
is-
elephant.
The random variable X would be the sample,
Oh, that's an X bar?
X, Y, yeah.
No, that's just an X.
Which number is that?
Number 2. X is the weight of one elephant. All in favor? A member of the population. One elephant out of the population. That's not important. This is what Wachowski likes to do. Don't worry about it. And X bar is the
Sample mean.
mean of the sample, okay? And she likes to say X is the weight of one member of the population. That's what her notation is. Which distribution would you use for this? Well, you don't know yet, but you've got a T distribution or a Z distribution. So since you haven't come to the T distribution yet, then you're going to use the
Z.
Z distribution. Good. Now, construct a 95% confidence for the mean weight. State the confidence interval, sketch the graph, and calculate the error bound. Go. I'm going to sit and you guys do it. This is the nuts and bolts, meat and potatoes type of problem in this section. It's the one you have to be able to do before you can do any of the fancy ones. So when you get yours worked out, please come up and show it to your classmates on the board of white. And we've got 5 people, and 1 board should be sufficient. So we want a nice graph. And we want it to have 2 ears. Oh, we have 6 people, so Lynn, you put yours up too, would you please? So 2 people to a panel. Okay, go. There's markers on the board if you don't have yours. So take 1/3 of a panel so that we all fit. Please. There's that's a nice one. according to you,